So, today we're going to look at 8.5 Part 3. So it's really the last section that we're going to look at that has anything about 2D. And then tomorrow we'll start looking at 3D. So the name of 8.5 Part 3 is dot product. And the dot product is the first time we're actually going to take a look at taking a vector and another vector and multiplying them together. Now, we've looked at products, but we've never looked at products of vectors. We looked at something like this. Anybody remember what that was called?
Scalar.
That's a scalar product. That's the product of a number and a vector. And it can make it longer, shorter, or flip the direction. Well, dot product is when you actually take one vector and you dot it with another vector. Okay? That would be pronounced v dot w. That's how you say it.
You wouldn't say like times?
No, you can't say times.
Okay. It's so weird.
So, let's say you had two vectors. Okay, each one of these vectors has horizontal components and vertical components. When we do an actual problem, the A1, the B1, the A2, and the B2 would all be numbers. Right, so like 3i plus 5j and negative 8i plus 7j. And here is how you find the dot product of two vectors. It's going to depend on these four numbers, A1, A2, and then B1 and B2. So to find the dot product, the first thing you have to do is take the horizontal components and multiply them together. So A1 is a horizontal, A2 is a horizontal. We're going to multiply those together. Then, we're going to add one more calculation. We're going to take the vertical components, and we're going to multiply those together. So B1 is the vertical component for V. B2 is the vertical component for W. Multiply B1 and B2 together. And that's the formula for finding a dot product. So it's really three things. A multiplication, another multiplication, and then an addition. Yep.
Where's I and J?
So, what are A1 and A2? What did I say earlier? Those are what?
The horizontal components.
Numbers.
Yeah, even more generally, they're just numbers. So, what do you get when you multiply a number by a number?
A number.
You get another number. Now, B1 and B2, what are those?
Numbers.
Those are numbers. And when you multiply two numbers together again, you get a number. So you're going to have a number from this part and a number from this part. And what do you get when you add a number to a number? You get a number. So the answer to your question is this is not a vector. It's a single number. So there is no I and J in the final answer. So an example of a dot product answer would be 10. Just that's it. Just a number. We're going to do some things with that number. That can be a little harder. But finding the dot product itself is very simple. Questions on the formula? Now, I didn't really get into it, but I said to you, you have to pronounce this as v dot w. You don't say times. And that's because vectors is one of the things in math that when you multiply them together, there's more than one way to do it. If you said to me, take the number 3 and the number 2 and multiply them together, there's only one answer you can get. Well, if you said, take the vector v and multiply it by the vector w, I'd have to say you need to be more specific. When you say multiply v and w, do you want me to multiply them as a dot product? Or do you want me to multiply them as a cross product? And there's a difference between the two. Dot product is what we're going to learn today. Cross product is what we're going to do tomorrow. So that's why you have to say dot, so I know what kind of multiplication. Now, technically, we're only working in 2D. So I know that it's dot product because cross product doesn't exist in 2D. That's the one thing. You cannot do this in 2D. So if you had two-dimensional vectors and you said multiply them, well, it has to be a dot product. It couldn't be a cross product. But it's still a good idea to make sure you, if you're gonna write down like an answer, you wanna do it like that. Use your symbol for dot. Also, this is one of the few times, like in math, they usually tell you don't use the x for multiplication, especially in algebra, because the x could be a variable. But when you write cross product, you can use the x. You have to. That's the symbol for cross. What I generally do to make it clear is I just make it small. I don't make it the size of a variable. Just make it a small cross, and then it looks like it's an operation and not a variable. All right, so let's try finding a dot product. So, v dot w. What are the first two numbers I'm going to multiply together to do that?
2 and 5.
So we're going to do 2 times 5. What comes right after the 2 times 5?
Negative 3 times 4. Or plus.
Before that,
Plus.
plus. And what comes next?
Negative 3.
Negative 3 times 3. And that gives me a dot product of how much? 1. 10 minus 9. And in a little bit, we'll see what you can do with that 1. This 1 allows you to do something. We'll see. All right, so that's v dot w. Let's try w dot v. If I write it as w dot v, very, very specifically in that order, what would I write down first?
5 times 2.
I'd write 5 times 2 plus what?
3 times negative
3 times negative 3. And what's that going to be?
1.
It's still 1. So what do you think that means about the dot product?
Doesn't matter.
It's commutative, yes. It's not necessarily a proof, it's an example, but it is true in general that if you switch the order that you do a dot product in, you will get the same answer. With cross product, that's not true. If you switch the order, you get a different answer. So that's one of the few times where multiplication is not commutative, when you do cross products with vectors. And we'll see that tomorrow. All right, let's try v dot v. So we're dotting v with itself. What would be the first two numbers you multiply together?
2 times.
So you do 2 times 2 plus, what will come next?
Negative 3 times negative 3.
Negative 3 times negative 3. And that's going to give me 4 plus 9. 4 plus 9, which is 13. Now, what's another way of saying 2 times 2? Besides 4. I'm looking at a shorter way to write the
2 squared.
the calculation out. 2 squared plus.
Negative 3 squared.
Now, you took a number and you squared it. You took another number and you squared it. You added them up. Does that seem similar to something we've done earlier? We're missing one thing. But it's kind of like Pythagorean theorem, except you didn't take the square root. You squared one number, you squared another number, you added them up, you just didn't take the square root. Let's see if that works with w dot w. If we were going to find the magnitude of w, it would be this. The square root of 25 plus 9. Now, let's do w dot w. 5 times 5. Plus 3 times 3. So it comes out pretty similar to finding the magnitude, except you didn't take the square root. So What does that mean? Well, that means that if you dot a vector with itself, you don't get the magnitude of it because you didn't take the square root. What you get is the magnitude squared. So anytime you dot a vector with itself, you're getting the magnitude squared. Any question on that idea? And then if you actually took it one step further and you did the square root, then you get that. The square root of a vector dotted with itself is its magnitude, because now you're taking the square root. And it was the same thing with w.w, so we don't have to write that another time. Let's try this one. So the vector 2, 6 dotted with the vector 0, 0. What's that going to be? 0 the number or 0 the vector? Number. Anytime you do a dot product, the result is a number. Okay. So the answer here, 0 the number. Question on that? All right, so dot product is distributive. You can do a distributive property with a dot product. So if you had an example and you had to add two vectors together and then find the dot product with that sum, you could do the sum first and then do the dot product with the result of the sum. Or you could distribute the dot product to each vector and add the result at the end after doing the two separate dot products. So that's basic distributive property, and it does work with dot product. If it ever comes up and you want to do a problem that way. So the real use that we're going to see for dot product is to calculate an angle. That's what dot product is used for. Find an angle between two vectors. Now, there's really two things in this lesson that can be time consuming. One of them is proving the formula for where the dot product comes from, and the other one is a word problem. So I really can only pick one or the other. So I don't think we're going to go through the proof of the formula for the dot product. Okay, so we're going to just use the formula. I'll show you how to use it, and then we'll do an application that's a word problem. So if you want to find the angle between two vectors, you have to figure out three things. First thing you have to figure out, and this is going to go in the numerator, is the dot product. The other two things you have to figure out are the magnitudes of each vector. The magnitude of u, the magnitude of v, those go in the denominator and are multiplied together. And that's not equal to the angle. It's equal to the cosine of the angle. So let me make a quick sketch instead of actually going through the proof. Like I said, I was going to skip that. And see if you could figure out a way to find the angle between two vectors if you didn't know this formula. Because you guys should know enough now that you could figure out an angle between two vectors without this. This is easier. This kind of gives you a shortcut. Dot product over the product of the magnitudes equals the cosine of the angle. But let's say you had something like this. Where's my background? There we go. So let's say we had, I don't know, a vector that goes like this, and another vector that goes like that. How do you think you could find this angle between the two vectors? Yeah?
You find the magnitude of those two and then you do tangent.
All right, you definitely could find the magnitude of each one because you know where they start, you know where they stop, basic distance formula, right? You know where this one starts, you know where this one stops. So these two sides could definitely be found. No question about that. But you said something about tangent. That would only apply if we had a right triangle. So right now we don't even have a triangle, but I think that might be on the right track. Yeah?
Can't you do side, side, side?
Well, yes. You could draw this third side in, and you could definitely find the length of it, because you know where it starts, you know where it stops. Use the distance formula. And then, once you know all three sides, this is a side, side, side triangle. Does anybody remember which law we used with side, side, side? Yep.
Law of cosines.
Yep. You could just do law of cosines, find this angle, and there you go. Now you've got it. And the fact that you use law of cosines to do that is where this cosine is coming from. So, at least if you understand that, you know why the cosine is here, because you use law of cosines. All right. So, any questions on that formula? All right, let's try an example. So, find the angle between U and V. So what I like to do first is find the three things that you're going to plug in. Find the dot product, find the magnitude, and then find the other magnitude. So can somebody tell me what my calculation is going to be for the dot product? Yep.
4 times 2. So
4 times 2
plus negative 3 times 5.
plus negative 3 times 5. And that's going to give me a dot product of
-7.
-7. All right, so we got our dot product. Next thing we need is the magnitude of U. Let me see if I can move that up and keep it on the screen. Yep. All right. Can someone else tell me how I'm going to set up the calculation for magnitude of U? John?
Would it just be, what, 4 squared plus 3 squared? Or negative 3 squared?
Plus negative 3 squared. Like that?
Yeah, and then the square root.
And then the square root. Okay, so Caleb, what's the magnitude of U going to be?
5.
5. Doesn't always come out to a nice number. This time it did. And Madison, can you tell me my calculation for the magnitude of V?
Square root 2 squared plus 4 squared.
All right, and that's going to give me the square root of 29. All right, so now don't round any of that, just leave it just like that. I've got everything I need to find my angle. Okay. What goes on the left side of my formula?
Cosine theta.
Right, cosine theta, and this cosine is coming from the fact you would have to use law of cosines if you did it all out, you know, the way I showed you earlier. All right, what goes in the numerator on the right side?
7. Or negative 3.
So dot product. And what goes in the denominator?
5 times square root of 29.
5 square roots of 29. And now, we just have to get theta by itself. So what would we do to get theta alone? Inverse cosine. So inverse cosine of negative 7 over 5 square roots of 29. All right, let's see what we get. Inverse cosine. Make sure when you do your denominator, I would open another set of parentheses because you have a calculation and you want it to do that calculation first. Right? A fraction bar is like a grouping symbol. Do the bottom part, do the top part, then divide them, then do the inverse cosine. So 5 square roots of 29. Close your denominator, close your inverse cosine, and you get an angle of 105.07. And that's your angle between the two vectors. Now, technically there's two angles. Right? If you draw two vectors, you have this angle that's inside, and then you have this one that's outside. We are always finding the one that's inside. Okay? Think of it like a triangle if you made it. It's the angle that's inside the triangle. Okay. Question on finding that angle? All right. So there are two special cases when we're talking about the angle between vectors. One of them is if the angle comes out, so they're 90-degree angle. And what do you call it when two sides meet at a 90-degree angle? The sides are
Perpendicular.
perpendicular. So with sides and with rays, they generally use perpendicular. But for some reason with vectors, they just call it orthogonal. Okay, but it means the same thing. So if you see on the homework or on the test, are the following vectors orthogonal? It just means, is the angle between them 90? Now there is a quick way to figure that out. So if they're orthogonal, what did you just say the angle would be? 90. So think about that for a second. This is the formula to find the angle between two vectors. You have an angle here, you have a dot product here, and you have a product of two magnitudes in the bottom. Let's pretend that you already knew the angle was 90. So if they're going to be perpendicular, that means the angle would be 90, which means this left-hand side would come out to what? What's the cosine of 90? 0. So if two vectors are perpendicular or orthogonal, the angle would be 90. If the angle is 90 and you fill it into cosine, you get 0 on one side. I don't know what's on the other side, I don't know the problem. But I know I would have 0 on the left. But that's all I need to know. Because if I have a fraction equal to 0, what does that mean about my fraction? No? So that means there's a 0 in the top, which specific to our formula would mean what? John?
The dot product.
The dot product was 0. If the dot product comes out to 0, the numerator comes out to 0. If that comes out to 0, the whole fraction is 0. And if that fraction is equal to 0, then that means the angle must be 90. And if the angle is 90, that means orthogonal. Alright, so that's a quick way to figure out if two vectors are orthogonal. All you have to do is find the dot product. Alright, so let's try an example. See if the following two vectors are orthogonal. Alright, what's going to be my dot product there? 4. So are these vectors orthogonal? No. What is the angle between them? Well, that I don't know. I'd have to finish the problem and find the angle. But I can tell you that they are not orthogonal. Can somebody tell me one thing that you could change to make these vectors orthogonal? You can only pick one thing to change. Yeah,
-2,
which one?
the bottom one.
Yeah, if you made the bottom one a -2, now you would have 2 times 1 and 1 times -2. So the dot product would be 2 minus 2. Basically, if you change any one of those to a negative, then you've just made the vectors perpendicular. So any questions here about why the answer is no? All right, so that's orthogonal. One other case we can look at is when the vectors are parallel. What do you think the angle between two vectors would be if they're parallel?
0.
All right, it could be 0. That would be like basically doing something like this. There's an angle of 0. If you move it up, you can see it. But there's an angle of 0 between those two vectors. There's also another angle. Well, 360 would be the same as 0. What other angle could we have between those two vectors and they would still be parallel? Yep. 180. If you had a vector like this and a vector like this, those two vectors are parallel. They're pointing in opposite directions. And if you move it over here, then you could kind of see it a little easier. The angle is 180 between them. And the angle here is 0. Right? So those are the two cases you can have for parallel. Well, let's see if there's a shortcut for that. So it could be 0 or 180. Let's set each of those up in our formula and see what happens. Cosine of 0 equals, you'd have a fraction, cosine of 180. All right, let's start with cosine of 0. What's the cosine of 0? 1. So if the angle between two vectors is 0, and you fill it in for your cosine, that means the left-hand side would have to come out to a 1. That's the only way you could get an angle of 0. Well, to make the left-hand side come out to a 1, what would have to happen on the right? Yeah. Right. The numerator and denominator would have to be the same number, and unfortunately, to figure out if two things are the same, you need to know each of them. So you have to find the numerator and you have to find the denominator and see if they're the same. Now, if we had 180, what's the cosine of 180? -1. And if the angle between them is 180 and you fill it into cosine, that means the left-hand side would be -1. How can a fraction give you -1? Caleb?
Numerator and denominator have to be opposites.
Right. Numerator and denominator have to be opposites, which again, unfortunately, to figure out if two things are opposites, you have to know both of them. So you'd have to find the numerator and the denominator. So there really is not a shortcut for figuring out if they're parallel, quite like if they're perpendicular. Right? But at least we understand what we're looking for. A numerator and denominator that are the same or opposites. All right, so let's determine if these two vectors are parallel. So we're going to need the numerator, we're going to need the denominator, so we might as well set this up like we're doing the whole problem up. I'm just going to move this up. Okay, calculation for my dot product. first two numbers, bless you, multiply together.
4 and 20.
4 times 20. Plus, next two numbers,
5 and 25.
Negative 5 times negative.
Oh, sorry.
negative 5 times negative 25. That's why I put parentheses so we don't confuse it with subtraction. And 4 times 20 gives me 80. 5 times, with the negatives cancel, 5 times 25. And when you add that up,
205.
205. Okay. So at least I know what I'm hoping for. I'm hoping if they're parallel that I get a denominator. Well, normally I would say it either has to be the same or be the opposite. But think about what we're finding in the denominator. You're finding the magnitudes. Magnitudes are always going to be positive. So either the denominator comes out to 205 or they're not parallel. Okay. So let's see what happens. Magnitude of V. That would be the square root of what plus what? 16, yep. 25. So that's the square root of 41. All right, and the magnitude of W. Let's see, what's 20 squared?
400.
So 400. And what's 25 squared? Anyone know that one? 25 squared?
Wet 2050. Something like that.
How much?
625.
625. So that gives me the square root of 1025. Okay. I need to find the product of these two magnitudes because that's my denominator. So let's do magnitude of V times magnitude of W. All right, so we've got square root of 41 times the square root of 1025, and that gives me a denominator of 205. So my numerator is 205, my denominator is 205. Are these vectors parallel? Yes. Specifically, what's the angle between them?
0 degrees.
It's the 0 degree case because it's equal, I forget where I did it, right here. It comes out to 1. Right? So what's the question? Determine if they're parallel. So the answer is yes. And if I asked you to be a little more specific, you could say the angle is 0 degrees. Questions on that one? Yep.
Just so I'm clear, when you multiply the square roots, what's going on with that?
When you multiply the square roots?
Yeah.
Well, technically you could do this. This is fine.
But that's so goofy.
That's not how I typed it in on the calculator, but that's the same thing.
Yeah. Okay. Fair enough.
So you're just multiplying two radicands together and then taking the square root. Other questions on that? All right. Last problem. So this problem is definitely going to lend itself to a sketch. And it's going to involve a little bit of the velocity vectors from yesterday, not the static equilibrium. We could switch it. Do you want to do the static equilibrium instead?
Oh.
No?
Well, is it going to be on the test? That's the question.
This is probably a better one to do.
Yeah, then we'll do this one.
Okay.
That sounds good.
Yeah. So we've got an airplane that's maintaining an airspeed of 500 miles an hour. Just to explain the difference between you're going to see two words in this problem, airspeed and ground speed. There's a difference. Airspeed is basically, you put your hand out the window, how fast the air is hitting your hand. That's airspeed, right? So, like if you were on the highway, you were going 60 miles an hour, and the wind was coming at you at 60 miles an hour, and you put your hand out the window, it's going to feel like the air is hitting your hand how fast? Like 120. So the air speed, like if you, or you put, a device that measures wind speed out the window, thing's going to register 120 miles an hour. But your speedometer is only going to say you're going 60. That's your ground speed. Does that make sense? So ground speed is, another way you could think of it is if you could point like a radar gun at an airplane and see how fast it was moving across the sky. That's its ground speed. But if you stick your hand out the window, the air speed might be different. So air speed versus ground speed. And the airplane is maintaining an airspeed of 500 miles per hour south. Now, it's flying, but there's a wind, there's a jet stream. And the jet stream is 80 miles per hour northeast. That means it's, how can I say it? That means it's blowing in a northeast direction. The wind is coming from the southwest, and it's blowing towards the northeast. That's where the wind is coming from and where it's blowing to. So in this case, is the jet stream helping the plane along?
No.
No. The plane's trying to fly south, and it's got something that's trying to push it northeast. So what I want to do is find the actual speed of the plane, taking into account the fact that the wind is hitting it. So like the ground speed, if somebody pointed a radar gun at it and got the speed of it, I want to know that. And I want to know the actual direction of the plane relative to the ground, because the plane is being blown off course a little bit. Okay? It says it's going south, but the jet stream is blowing northeast. All right. So with all this information, what did I suggest the first thing we do is?
Picture.
Yep, I'm going to make a picture. How many different vectors do we have in this problem?
Two.
Just two. You have a vector, the plane has a speed in the direction, and the wind has a speed in a direction. So two. And I basically want to figure out what happens when I combine those two vectors together. So essentially, this is an addition problem with two vectors. That's all it is. But we have to turn this into vectors, because right now we have speeds and we have compass headings. Well, to turn that into vectors, the first step is going to be figure out angles, and then we'll go from there. All right, so let's start by drawing a velocity vector for the plane. What direction is the plane traveling? South. So the plane is traveling south, and let's let that be the velocity vector for the plane. So I'll call that v sub p. Now I need a velocity for the wind. We'll call that v sub w. What direction is the jet stream blowing in?
Northeast.
Northeast. And when I say northeast, I mean exactly northeast. So if you think of a compass, this is east, this is north, and the jet stream is northeast. Now, we don't want to draw it as powerful as the plane, because it's 80 miles an hour, the plane is going 500. It doesn't have to be to scale, but it should be shorter. So there's our velocity vector for the wind. Now, visually, what's going to happen here, I can show you on the smart board quick before we do numbers. You're going to put the wind vector on the end of the plane, and this is going to end up being the actual thing you want to find. That's what you want. The length of that black vector is going to be the real ground speed of the plane, and the angle that it's tilted at is the angle that it's really going to be flying at when the wind pushes it off course a little bit. So this is what we want to figure out numerically. There's a visual for what you're trying to find, that thing in black. So what we want to do is represent each one of these arrows as a vector that we can turn into i's and j's and add them up and get this one in black. All right, let's start with this one. So this is going to be the velocity vector for the wind. What's the magnitude of the wind? All right, so the magnitude is 80 miles per hour. And what would the angle be? It's always, the angle is always with the east-west line.
45.
It's a 45-degree angle. Now use what we learned yesterday and turn that into a velocity vector. Magnitude, what trig function do we use for the horizontal? Cosine. I plus magnitude, what trig function do we use for the vertical? Sine 45. Okay. All right. So now we're converting v sub w into a unit a velocity vector. All right, well, decimals are fine. We don't have to do the root 2 over 2 thing for cosine 45. Let's do 80 cosine 45, 56.57. There's the horizontal component of the wind. And the vertical, well, it's going to be the same thing because the sine and the cosine of 45 is the same. So it's 56.57 J. All right, so we'll come back to that. We're going to need that once we figure out the velocity vector for the plane. Okay, velocity for the plane. What's the magnitude of the plane? Okay, magnitude is 500 degrees, or 500. And what's the direction again? South. So yes, that's a 270 degree angle because it's south. Okay, let's figure it out. So we're going to have 500 cosine 270. That's the horizontal. And 500 sine 270 is the vertical. Now, is the plane just the red vector? Is the red vector pointing left or right at all? No, then it shouldn't have a horizontal component to it. And when you do the cosine of 270, you get 0, which makes sense because the red vector is perfectly vertical. So this component disappears. That means all of the component is going into the vertical, so we should end up with negative 500 because negative means it's going down. Let's see. 500 sine 270 gives me negative 500. So there is the velocity vector for the plane. Now, let's call this vector in black v sub a. V sub a for actual. That's what's actually going to happen. And remember how we calculate v sub a. It's the sum of the vector for the plane and the vector for the wind. So now sum them up, add them together. Take the wind, add the plane, and you'll get the actual. All right, so for the wind, what's that one? 56.57i, got it. Well, when I add the plane and the wind, are there any I components to add together? No. So it's going to stay 56.57i. Are there any J components to add together? Yes. 56.57 minus 500. So it's going to slow the plane down a little bit. So it's negative 443.43. Okay, and the two things, so now you have the vector in black. Any question on how we got that? Now, one thing they wanted to know is, what is the actual ground speed of the plane? Well, that's that. It's the magnitude of the vector in black. Tell me how long that black vector is. So it's going to be the square root of, actually, you know what? We can probably just do it all at once. What do I do with the 56.57? Square it. Plus, just make sure it all stays under the root. Negative, well, it doesn't matter if you use the negative, because when you square it, the negative is going to go away. And honestly, it's just one less symbol I have to type. 0.43 squared. So the actual ground speed of the plane, taking into account the wind, is 447.02 miles per hour. So there's the ground speed. Now, the other thing they wanted to know was the angle. Okay, well, the angle, what did they want to know again? With the direction, okay. Well, to find the direction, you have to figure out what angle this vector in black is at. So there's a couple ways you could do it. You either could find this, or you could find that. If you find one, you'll know the other automatically. But you have to figure out one of those angles. Since we've been practicing finding angles between vectors, let's set it up to find that one. So that's the angle between what two vectors?
VP and VA.
VP and VA. So we want to know the angle between them. And then once I know that, I can say the direction of the airplane. It would be 270 plus the amount of this angle. That's the direction that the plane's going. It's probably like 290, something like that. The angle between VP and VA. All right, we need the magnitude of each one. We already have one of them. So the magnitude of VA, that saves us a little time, 447.02. The magnitude of the plane, actually that one's pretty easy. What's the length of that line in red? 500. So I think the only thing we're going to actually calculate is the dot product between VA and VP. So this is VA, this is VP. If it confuses you because you don't see the I, then think of it like this. Multiply the I's together. What's 0 times 56? That's 0. Now the J's, negative times negative is a positive. I need 500 times 443.43. 500 times 443.43. That's a dot product of 221.7. Did I type that right? I'm just surprised it came out without a decimal. Yeah. 221.715. And lastly, my angle, use your inverse cosine. Inverse cosine of the dot product, 221.715, divided by the product of the magnitudes, 447.02 times 500. And this should come out pretty small. It should probably be like 20, 25 degrees at most. Or even smaller, okay. So it comes out to about 7.27 degrees. So that means the actual direction of the plane is 270 plus, what did we just get?
7.27.
7.27. So actual direction is, you know what, you could say it this way, 7.27 degrees east of south. 7.27 degrees to the right of south. I just say it that way. Alright, so, I don't know, maybe not as bad as the equilibrium problem, but there's still some moving pieces in that one we gotta figure out. I would never give you a direction that's random. Okay, the wind is either gonna blow northeast, northwest, southeast, southwest, northeast, southeast. It's gonna be one of those basic directions. Okay? All right, so homework tonight is 7 to 17 and 25. On 7 to 17, each question asks three things. I think it asks you to find the dot product, the angle, and then determine if the vectors are parallel, perpendicular, or neither. So all the parts are related. And then 25, that is a word problem about airplane and a jet stream. Just a reminder, I will be after school tomorrow in case anyone needs extra help or has to make anything up.